Welcome back. I have a long table here. You can see its dimensions in the image. And on the table, I have 3 blocks of concrete. Let it be block 1, block 2, and block 3. Block 1 has uniform height, and the same thing goes for block 2 and block 3. Their heights are uniform, meaning that this edge is as high as this edge here. And we also assume that they all have uniform mass. The mass of block 1 is 450 kilograms. The mass of block 2 is 300 kilograms. And the mass of block 3 is 375 kilograms. Let's simplify our lives and assume that G is 10 meters per second squared. That means that Fg1, the force of gravity of block 1, equals m1 times g, which equals 4,500 newtons. Then Fg2, the force of gravity of block 2, it equals m2 times g, which is 3,000 newtons. And then the force of gravity of block 3, Fg3, it's m3 times g, and that's 3750 newtons. And these force vectors, they would be applied in the middle of block 1, block 2, and block 3, because remember, their mass distribution is uniform. But of course, the table does not experience 3-point forces due to those blocks. It experiences force distribution over the entire table. Block 1 covers the area of A1 equals, and then here you have 2 meters, the width of the table, and here you have L1, which is 3 meters. So 3 times 2, that would be 6 square meters. So block 1 covers 6 square meters of the table. Then block 2 also covers the area of 6 square meters. Again, the width of the table is 2 meters, and L2 is 3 meters. Finally, block 3 covers the area of 3 square meters. The width of the table is 2 meters, and then L3 is 1.5 meters. So the distributed load or force pressure due to block 1 is P1 or pressure 1 equals the force of gravity due to block 1 over the area that the block 1 covers, A1, that would be 4,500 over 6, which is 750 newtons over meter squared, or in other words, 750 pascals. Then the same thing can be calculated for block 2. P2 equals the force of gravity due to block 2, the area that the block 2 covers, so it's 3,000 over 6. It equals 500 newtons over meter squared. In other words, it's 500 pascals. And finally, you have the same thing for block 3. P3 equals the force of gravity due to block 3 divided by the area that block 3 covers. You have 3750 over 3. That's 1250 newtons over meter squared. In other words, it's 1250 pascals. You can graphically depict this force distribution like this. Lots of equally spaced arrows going down. This one is pressure 1. It belongs to this distribution. Then pressure 2 belongs to this distribution. And pressure 3 belongs to this distribution. The more pressure there is, the longer the arrows are. You can see that pressure 2 has the smallest number, 500 pascals, and that's why the arrows are the shortest. then comes pressure 1. Now the arrows are longer. And finally, pressure 3. It's the biggest, so the arrows here have the highest length. And the fact that the height of all the arrows per block are the same means that the force distribution per block is uniform, which makes sense because each block has uniform mass distribution. It doesn't have some sections that are heavier than other sections. The mass is distributed equally in each block, and also each block has uniform height. It's a cuboid. Each block is a cuboid, and that's why the pressure distribution in this location is the same like in this location or in this location, so the arrows will have the same heights in all of these locations for pressure 1. Now, if you remember, then block 3 has less mass than block 1. Thus, FG3 is smaller than FG1. However, FG3 is distributed over a smaller area compared to FG1. Therefore, the force distribution for block 3 is greater than for block 1. So P3 is greater than P1. And that's why the distribution arrows in P3 are longer than in P1. Now, the thing is that representing this force distribution like this in 3D is extremely tedious. However, if you go along the length of the table, so in this direction, then your pressure distribution changes. You first have P1, then you have P2, and then you have P3. But if you go along the width of the table, then your pressure distribution does not change. So as you go along the length of the table, if you are at the location where you have P1 as your pressure distribution, then this P1 is the same along the entire width of the table. And the same thing with P2 and P3. It does not change with the width of the table, only with the table's length. And in fact, in statics, it's very common that load distribution changes in one direction, but it stays constant in another direction. And that allows us to simplify the representation of our force distribution. Since the width of the table is d equals 2 meters, then I will do the following. For block 1, I will have W1 equals P1 times D, so 750 newtons over meters squared times 2 meters. Then the meters here get cancelled out, and you will have 1,500 newtons over meter. Then for block 2, I have W2 equals P2 times D, 500 newtons over meter squared times 2 meters. Again, I cancel out the meters, and I will have 1,000 newtons over meter. And finally, for block 3, I have W3 equals 1250 newtons over meter squared times 2 meters. The meters are cancelled, and I have 2,500 newtons over meter. The thing is that W1, W2, and W3, they are also distributed loads, but only in one direction, only in the direction of the length of the table. And the reason for why I did that is because now I can represent this table and this distributed load in 2 dimensions in this way. You can see that this is your table, but now you only see the side view of it. So this edge here that you can see, it's this edge here. So you're looking at this table from the side. Here I only represent the length of the table. Here you have L1 equals 3 meters, L2 equals 3 meters, and L3 equals 1.5 meters. And this here, that's your W1 equals 1,500 newtons over meter. That's your W2, and that's your W3. As you can see, it's a lot easier to represent force distribution in one direction, in newtons over meter, instead of newtons over meter squared. Now, note that even though I have omitted one dimension, the width, I haven't lost any information, and that's because the pressures in 3D were multiplied by the width of the table. You see, W1 equals P1 times D, then for W2 I had P2 times D, and for W3 I had P3 times D. If I work with pascals, or newtons over meter squared, where I show the entire table in 3 dimensions, then if I multiply those pressures by their respective areas on the table that those pressures cover, you get your entire forces of gravity for your blocks. So Fg1 equals P1 times A1, so you have 750 newtons over meter squared times 6 meters squared. Now the meter squared, they get cancelled, and you're left with 4,500 newtons, which is exactly what you have here. Then Fg2, you get it in the same way. P2 times A2, you have your pressure times your area. You cancel out the meters squared, and you get 3,000 newtons, which is what you have here. Finally, Fg3 equals P3 times A3. Again, you take your pressure distribution, you multiply it by the area that is covered by this P3 pressure distribution. The meters squared get cancelled, and you get 3750 newtons. And by the way, the location of these gravity forces are in the middle of their pressure distributions. So first of all, in terms of width, all these force of gravity vectors, they are in the middle of this width. 1 meter from one side and 1 meter from another side. Then, in terms of length, since you have 3 meters for block 1, Fg1 is located at 1.5 meters from the beginning of this table. So in this image, it would be somewhere here. Then, this Fg2, it will be somewhere here in the middle of block 2. So you had 1.5 meters here, then 1.5 meters here. And since block 2 is also 3 meters long, and you divide this length also by 2, then you will also have here 1.5 meters, and on the other side you will have 1.5 meters, which means that from this location here till this location here, you have 1.5 plus 1.5, you will have 3 meters here. And then finally, Fg3, in terms of length, will be located in the middle of this L3. So the Fg3 vector, in terms of length, will be somewhere here. And since L3 equals 1.5 meters, that means that this length here, it will be 0.75 meters, and also this length here it will be 0.75 meters. So if you now want to go from this point here till this point here, then you will have 1.5 meters, which you have here, and 0.75 meters, which you have here, which means that the distance between FG2 and FG3, it will be 2.25 meters. That's this distance here. So these are the 3 point forces that correspond to their respective pressure distributions. And the locations of these point distributions, they are like this because the pressure distributions are uniform. P1 is the same here and here and here and here, everywhere. Then also P2 is the same here and here and here and here and in other places. And also P3 is the same here and here and here and in all other places where you have block 3. And so you know the locations where your point forces are applied to, and you know what your point forces are because you took your pressure distributions and you multiplied them by their respective areas. But I will get the same forces if I work with my simplified distribution diagrams. So I take Fg1 equals W1 times L1, so this one times this one here, so 1,500 newtons over meter times 3 meters, the meters get cancelled, and you have 4,500 newtons. Then Fg2 equals W2 times L2, so this one times this one, you have 1,000 newtons over meter times 3 meters, the meters get cancelled, and you have 3,000 newtons. And finally you have Fg3, W3 times L3, 2,500 newtons over meter times 1.5 meters. You cancel out the meters, and you have 3,750 newtons. And now, since the distribution for each block in terms of length is constant, you know that these point forces, they will be applied in the middle of their respective length distributions. So again, here you have 1.5 meters, here you have 3 meters, and then here you have 2.25 meters, just like you had it here. And now, as you can see, you get the exact same forces. Whether I multiply pressures and areas or these unit length distributions by their respective lengths, it doesn't matter. I get the same forces. And that's because when I went from pascals to newtons over meters, in other words, I went from newtons over meter squared to newtons over meter, I had already multiplied my P1, P2, and also P3 by this D, which is the width of my table. That's why you don't lose anything with this simplified force distribution diagram, but it's way easier to draw it. Of course, you have to remember that all this works because your force distribution in pascals was constant along the width of the table. It did not change when you moved along the width of the table. If you have a general case where you have force distribution over an area that constantly changes, where your pressure changes all the time when your X or Y changes, then you can't do it that way. Then you have to integrate to get the total force. So if the pressure distribution is written as a function where P is your pressure or your dependent variable, and then x and y are your independent variables, then the total force due to that distribution is the following. F equals the area integral, then the pressure function times, and dA. Now dA can be written like this. dx times dy. Essentially, you will have some kind of differential area element here, which will be your dA, or dx times dy. And so you will end up having a double integral. You will have this case, and so you will integrate from your initial x to your final x. So your x initial, it will be in this location here, and then your x final, it will be in this location here. And so once you have evaluated this integral, you will also integrate it from y initial till y final. So your y initial, it will also be here, and then your y final, it will be here. And we will cover that later in this section as well. Don't worry about it right now. However, in statics, you very often deal with problems like narrow beams, for example, or problems of that nature, and there it is reasonable to assume that this pressure distribution only changes along the length of the beam, and it stays constant along its width. And as a result, instead of representing it like this, you could simply represent it like this. This would be in pascals or newtons over meters squared. And if you multiply that by the width of the beam, then you will have force distribution per unit length, which has the units of newtons over meter. That's why in statics, this representation is used very much, and this 3D Pascal representation, it's not used that much. And now, with that in mind, let's go back to our table, and particularly the simplified load distribution diagram, which you see here. And your task now is to replace this load distribution diagram with an equivalent resultant force vector. So the entire diagram has to be replaced by one single FR vector. No couple moments are allowed. So try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now replace our force distribution along the length of the table with one single resultant force, Fr. First of all, the force distribution is constant along the length of the table per block. Each block gives you different distribution, but per block it's constant. Your W1, W2, and W3, they're simply numbers. W1, for example, equals 1,500 newtons over meter. In the future, you might see other cases. For example, you might see that W1 equals 1,500 times L. If we say that L goes in that direction, then your force distribution would look something like this. It would increase with L. However, that's not our case. In our case, it's constant. Thus, the force resultants for each distribution must be placed in the middle of that distribution. And it makes sense because if we take block 2, for example, then you have W2 times L2 over 2, which is 1,000 times 1.5, which is 1,500 newtons. If you have that on the left side, then you would also have it on the right side, and then you add them together and you have 3,000 newtons, which is your Fg2. So Fg2 needs to be in the middle of this force distribution for block 2 because you have the same amount of force, 1.5 meters, on the left side from Fg2 and 1.5 meters on the right side from Fg2. And now you have to find the total resultant force and put it in the right place to make the system equivalent. So let it be Frg, the resultant force of all the gravity forces, it equals Fg1 plus Fg2 plus Fg3. From the previous video you already know that this here is 4,500 newtons, this one is 3,000 newtons, and this one is 3,750 newtons. So what you have here is this: 4,500 plus 3,000 plus 3,750, and it equals 11,250 newtons. Let's say that this point here, it's A, and this point here, it's B. We can first place this Frg vector at point A. In that case, we have to add the resultant moment about point A due to these three gravity point forces. So let me write MRA equals 4,500 times 1.5 meters clockwise. That's the moment about point A due to this force. Then you have plus 3,000 times 4.5 meters. That's also clockwise. That's the moment about point A due to this gravity force. You can see that now the moment arm is 1.5 plus 3 meters, so 4.5 meters. And finally, you have 3,750 times 6.75 meters. That's the moment about point A due to this force. And here the moment arm is 1.5 plus 3 plus 2.25, so 6.75. And of course it's clockwise. And so if you calculate them all, then you will get 45562.5 Newton meters clockwise. So this couple moment needs to be added here. This is your MRA. And then you simply calculate the correct position from point A like this. Frg times dA, that's your MRA. So you express your dA like this, and if you divide these two numbers, then you will get 4.05 meters. So if this is your dA, which is 4.05 meters, and you place your Frg here, you will represent the entire system with one force vector only. So this system is equivalent to this system, and then this system is equivalent to this system, and by the end of the day, all this is equivalent to this system, which is the real representation of the situation. Welcome back. In the previous video, we measured the location where we would apply this force from point A. But you will get the same location if you measure it from point B. So you put this force, Frg, at point B. Then you calculate the resultant moment about point B due to these three forces. So you have MRB equals 4,500 times 6, and now it's counterclockwise. So we are talking about this force here, and now here this distance, it's 0.75 meters. So you have 3 plus 2.25 plus 0.75, which is 6 meters. That's your moment arm. Then plus 3,000 times 3. We are talking about this force now, and the moment arm is 2.25 plus 0.75. And just like the first term, the second term is also counterclockwise. And finally, you have 3,750 times 0.75, it's this force, times the moment arm, which is 0.75 meters. And again, it's counterclockwise. So MRB equals 38812.5 Newton meters counterclockwise. And so I would have to add this moment right here. That's your MRB. And now we have FRG times dB, that's MRB. You express your dB like this. In terms of numbers, they look like this. And so in the end, your dB equals 3.45 meters. So I'm going to put my FRG right here, and that's my dB, 3.45 meters. Now the length of the entire table is L1 plus L2 plus L3, and that will give you 7.5 meters. So that's the entire length of the table, 7.5 meters. And then if I calculate 7.5 minus dB, or 7.5 minus 3.45, that's 4.05 meters, and that's the length from point A till this FRG force. And if you remember, then that's exactly what your dA was, which you calculated in the previous video. So that's your dA. In fact, you can take any point on the table. Let's take the point where your FG3 is. So you have 0.75 meters here, just like here. Let's call this point C. So the resultant moment about point C is 4,500 times 5.25 counterclockwise plus 3,000 times 2.25 counterclockwise. These were due to these two forces. And note that FG3 does not create a moment about point C because there is no moment arm there. And so in the end you have MRC equals 30375 Newton meters counterclockwise. So you would add this counterclockwise moment here, that's your MRC, and then you write FRG times DC, that's MRC. You express your DC like this, or like this, which will give you 2.7 meters. So if this is your point C, then now you are 2.7 meters away from point C. And then remember, here you have 0.75 meters, and that means that the entire distance here from the resultant gravity force till point B, it's again 3.45 meters, and then from point A, you have 4.05 meters. As you can see, you still end up in the same location on the table, 4.05 meters from point A. And that's how it works. Now note that for the table, it makes no difference whether I have this distributed loading here, or this case where my FRG as a point force is 4.05 meters from point A. However, that is only true for as long as we have our rigid body assumption. If we take away that assumption and we allow this table to deform, then it's not the same thing. Let's say in this case, the table will deform like this. And then in this case, it will deform like this. The table will deform slightly differently in each case. So when we have our rigid body assumption, then this case here, it's equivalent to this case here, which in turn is equivalent to this one here, and this is equivalent to this one, and this is equivalent to this one. But if we take away our rigid body assumption, then each single case is different, because in each single case, the table will deform differently. So that's what you need to keep in mind. Also, when you went from this load distribution to these point forces here, let's say that you went from W1 to FG1, then you calculated that like this. FG1 equals W1 times L1. So this one times this one. And now when you did that, then what did you really do? This W1 here, it's essentially a function that depends on L. It's a horizontal straight line function. Its value is 1500 newtons over meter. Again, since it's constant, it's a horizontal line. And then you multiply that by L1 equals 3 meters. Essentially, you have calculated the area under the curve. Essentially, what you have done, you have integrated it from L equals 0 meters until L equals 3 meters, when you keep your L as an independent variable. So this narrow strip here, it has a width of dl, and so this differential area here, it's W1 times dl, which is your differential force, dF. That's the meaning of this differential area here. And so now you would simply apply this integral to it. Fg1 equals, and then you integrate from L equals 0 till L equals 3, W1 times dl. So this is your integral. You can take out your 1500 from the integral because it's constant, and so you have 1500, and then you evaluate this integral from 0 to 3, so 1500, 3 minus 0, and that gives you 4500 newtons. So you multiply your W1 by dl, and dl is your infinitesimal length, and then you will get your infinitesimal force of gravity 1. And then as you integrate from L equals 0 till L equals 3, you will simply add up all these infinitesimal forces, and in the end you will get your total Fg1. So it's simply a very easy integration. But of course here, this area is not in square meters. It's rather in newtons. So the context matters. But now, what if I want to calculate the total moment about point A due to this force distribution W1? Well, each differential force element, dF, that you have here, it has a moment arm, which we can denote with a variable L from point A, because remember, this point here, that's your A, that's the corner of this table, or in this image, that's the corner of this table here. And so your differential moment about point A, let's call it dMA, due to W1, due to this force distribution, it will be L times dFg1. But you know that dFg1 is W1 times dl. So you have L times W1 dl, or simply W1 times L times dl. The greater your L, the greater your dMA. And so as you go through the length of the table from L equals 0 meters to L equals 3 meters, your total moment about point A due to W1, it's the integral of dMA due to W1, and you integrate that from L equals 0 till L equals 3. So you can rewrite it like this, or like this. Now L needs to stay inside the integral, because it's a variable, it's not a constant. And so you have 1500 over 2 times L squared, and then you evaluate that from 0 till 3, so you have 750 times 3 squared minus 0 squared. That will be 750 times 9. That's 6750 Newton meters. And so you have Fg1 and Ma due to this force distribution W1. And then you can say that Fg1 times dAW1, which is a variable for distance, it equals Ma due to W1. And so if you calculate this distance, 6750 over 4500, then you get 1.5 meters. And that's where you put your Fg1 force vector, right? You put it 1.5 meters from point A. Now, of course, you might ask, why did we go through such hassle, all the integrals, just to find something as obvious as the fact that Fg1 as a point force is applied in the middle of this W1 force distribution? Well, we did that because now, thanks to this approach with integrals, you know how to handle general force distributions. Let's say that you have some kind of general force distribution per unit length. So it looks like this, a general force distribution. Let's say that this is Li, L initial, and this is Lf, L final. So you have a general function in terms of L. And let's say that this is our origin, O. If you want to get the total force due to this force distribution, then this is the formula. F equals the integral, you go from Li to Lf, W times dl. So this is your differential area under the curve. This is your differential length. This here is your W. So the differential force element is W times dl. Then, if you want to get the total moment due to this force distribution about point O, then here your differential force is L meters away from point O. And so you write the total moment about point O equals, you integrate from Li to Lf, and now you have W times L times dl. This L here, that's this one here. And then, in order to find this special location where you would put your force F so that you could omit the moment altogether, this special location, we can call it L bar, is the location where you will put your resultant force for any general force distribution in order to make your system equivalent, and you calculate that like this. F times L bar equals MO, so L bar equals MO over F. In other words, this special location equals your moment integral divided by your force integral. Thank you very much.